Kia ora and welcome to a video about haloalkanes. So you can sit there and start singing the song if you want to. Halo, halo. No, maybe not. Okay, so haloalkanes are commonly also known as alkyl halides. Alkyl just meaning a carbon chain, and halides meaning the halogen side of it. This is where you have the alkane chain, so R and X. X can be chlorine, fluorine, bromine, or iodine. So they will be chloro, fluoro, bromo, and iodo. I quite like iodo because it sounds funky. We have a little section here on where to do some nomenclature. So I'm assuming that you can remember how to name these things from last year. The idea that you name the alkane chain and then you need to tell me which carbon number the halogen is on. And you should be able to remember from last year how to classify these things as primary or secondary or tertiary. Okay, remembering that the primary, secondary, and tertiary is depending on how many carbons the carbon that has the halogen is attached to. How many carbons is attached to that carbon? Just the same as alcohols. Okay, we've got a little short note here on physical properties. So the fact that boiling point increases with corresponding molar mass, so that's how heavy it is. I should really not say that, how much mass it has. If you want to know more information about that, on page 123 in your workbooks has a nice little description about that. And it is generally insoluble in water due to being non-polar. And that's where you can sit there and start yelling at me. Feel free to be yelling at me right now, because I'm trying to tell you here that halogens bonded to carbons are non-polar. Not so much. The bond of the carbon to halogen is polar, but because of the carbon-hydrogen chain, generally speaking, that being non-polar, haloalkanes are considered to be non-polar, and therefore they won't dissolve in water because water is polar. Okay. Making halogens, so how to prepare these things. Okay, so we have alcohols plus a hydrogen halide or thiochloride, alkanes plus hydrogen halogens in the presence of light, and alkenes plus halogens or hydrogen halides. So start off with an alcohol. So if I have, say, carbon with a chloride on it, okay, I can react that with a hydrogen halide. So I got this the wrong way. You should have told me again. OH, alcohols plus HCl will go, and this will be a substitution reaction. So I'll end up with this. Cl, that's an L, Cl plus HOH, which is commonly known as H2O, or water. Cool, so that's that one. Halogens, alkanes and halogens in the presence of light. You've done this one in class. This is an experiment we did with bromine water. So let's do the same one. So let's do propane. Propane with bromine, Br2. In the presence of light, we often draw light as being a squiggly line representing the fact that it is a wavelength. Okay, and that is a simple substitution reaction again. But this time I will have bromine instead of a hydrogen, and I will make HBr. Remembering that that is quite slow and generally faster in the presence of light, as opposed to the one we did in class with alkene. Oh no, we didn't. Yes, we did do alkenes. Shush, Mrs. Hay. Alkenes plus, again, we did it with bromine water, so I'll use bromine again here. Didn't need sunlight. It's fast, it's cool, it's awesome. You saw the color decolorizing from the bromine quite fast. So we have C's, tasty like these. And the bromine adds across the double bond. Sweet. Okay? Cool. Again, if you're stuck on that stuff, go back and review your notes from the previously. and it should have more about that. Okay, so reactions of haloalkanes, or haloalkanes. These are fairly reactive compounds due mainly to the polarity of the carbon-halogen bond. Haloalkanes can form amines when reacted with ammonia in ethanol or in just an alcoholic solution in a sealed tube. Haloalkanes can be readily converted to alcohols by substitution reaction and to alkenes by elimination. So not only can we make haloalkanes from alcohols and from alkenes, but we can actually go in the back direction as well. We can go backwards. Just to quickly momentarily talk about this polarity bizzo stuff. I'm again hoping that you'll remember that carbon and say a halogen. So if I had 3 H's off here, H, H, H. Okay, this chlorine is more electronegative, so it is, we say it is partially negative, and this carbon then is partially positive. So it creates this kind of polarity buzz going on. I'm not sure if you are used to drawing a vector. Okay, saying this is positive, that's negative. A vector, for those of you in physics, the vectors will just be sweet as. For those of you not in physics, it's just pointing towards the side that is more negative. Because the chlorine hogs the electrons in this bond here, so this pair of electrons here spends more time around the chlorine than the carbon, because the chlorine is more attractive. Okay, we will go over that again when we get to 3.4, but I just thought it might be quite useful to go through again now. Okay, again, if you want to know more about that, there is this whole section, lovely section about nucleophiles on page 1, 2, 3 in your workbooks. Oh, too fast. Right, so alcohol formation. Let's change colour. Right, alcohol formation. So, in general terms, we have, say, carbon, 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 carbon. I'm just going to stick with 3 again today. Carbon, 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 and say I have iodine on here, might be interesting. That plus an OH minus, so a base, an alkali solution. This OH minus, because this carbon here, we just said this, is partially positive, and this iodo is partially negative, then this negative business here can actually come in here and attack here and kick this off. Okay, so this will make substitution of C. If you really want to be fancy pantsy, you could call it nucleophilic substitution. So instead of the I on there, it is OH, and we make I minus. Okay, now primary and secondary ones of this, they are hydrolyzed to the alkali, or to the primary and secondary alcohol. So if I had this iodo was here, that would be secondary. Okay, so they go to the secondary, that would go to a secondary alcohol. Tertiary haloalkanes react faster, and that is a good way to distinguish. Okay, this is a good distinguishing test between these, is reacting primary, secondary and tertiary haloalkanes to the alcohols. Cool. Right. Brilliant. So yeah, primary are slow, secondary are faster, and tertiary are super duper fast, like super duper. We might see if we can do an experiment on that. We might, if we can have time to fit that in. Cool. Right. So moving on. Next one. Amine formation. Now, amine formation is a very interesting one because you can go from, alright, again I will start with my 3 C's, and maybe this time we will stick, what have we stuck on here? Let's go with just bromine, that's always quite cool. Now if I react this with just ammonia, okay, and if I had that ammonia in aqueous solution, you've got to remember that aqueous solution will contain a fair whack of OH minus, yeah? So if you think about this, if I had this in aqueous solution, the OH minus is probably going to be the one that will go in here and attack this rather than the NH3, because I'll have lots of OH minus. And if you can figure that one out, welcome to my class, because you are awesome. However, if we do this in heat and an alcoholic solution. So we dissolve the ammonia in alcohol, not in water, because that way there is no OH minus around. Then this will do a very nice substitution reaction, and I'll end up with the amine. Cool. Right. So we want to make sure that we don't have that water in there. Right, and again I will have HBr. Awesome. Moving on. Elimination reactions. Alright, this is some fun stuff. Pen. Elimination reactions. So these are the opposite of addition. So addition we add stuff on, elimination we eliminate stuff. So we go pretty much, we would go from here, and this is where I'm going to be a little bit cunning, hopefully. Actually, yeah, let's start with 4. No, let's start with 3. 3, okay, and there's my bromo on there. Okay, and there's a hydrogen on that one. There's hydrogens all around, but I'll just draw that one in just to make sure. So if we have this and we heat it up, this is the conditions, heat, and we have alcoholic, again not water, potassium hydroxide or sodium hydroxide. Okay, could be either, just a basic alcoholic solution. Then this will eliminate this H and this Br. So I will make C, C, double bond C, 2 hydrogens, 1 hydrogen, 3 hydrogens. So that HBr has been eliminated. Now, if I have, no, let's make it black, it's cool. If I have 4 carbons in a chain, so I have a butane chain, and then I have a bromine. Okay, this bromine has an option of going for this hydrogen or this hydrogen. Of course, there are this hydrogen, this hydrogen, this hydrogen, 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 all around there, so that's cool. Okay, so I can make 2 products here. I could make, eliminating the red one, let's change this into red. Eliminating the red hydrogen, I would have carbon, 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 4 carbons. If I've eliminated this and this, then the double bond will be here, there. 1, 2, 3, 1, 2, 1, 1, 2. Or if I eliminate the blue hydrogen, I will make 1, 2, 3, 4. This hydrogen here, so the double bond will be here. So I've made butane 2, but 1-ene and but-2-ene. Okay? Now, this is where we have what I will refer to as anti-Markovnikov. And yes, it is called anti-Markovnikov. Kovnikov. However you spell his name, he's got 10 billion ways. Alright, so the Markovnikov is the rich get richer, so the carbon with more hydrogens get the hydrogen. This is the opposite. So this is the poor get poorer. Poor get poorer. Sucks to be them. Alright. So the carbon has the least number of hydrogens. So this one has 3 and this one has 2. The carbon has the least number of hydrogens, loses the hydrogen more often. So this is actually my major product and this is my minor. Alright, cool, I'm pretty sure that's us. Check. Yes, it is us. Okay, join me again next time for a discussion about amines. See ya.